Hi, everyone. My name is Brandon Rodriguez, and I work in the education office at the Jet Propulsion Lab in Pasadena, California. Thank you so much for joining us again for this special bonus session on the upcoming helicopter flight of Ingenuity. Really glad to have you guys with us today. Perhaps you've participated throughout the last few weeks leading up to the landing of the Perseverance rover. And now we're joined by the amazing Taryn Bailey, who's going to tell us a little bit more about the next phase of this amazing scientific exploration that we're doing on Mars. So, Taryn, tell us a little bit about yourself.
Hi, yes, thank you for having me, Brandon, and hello to all the viewers out there. So my background is in mechanical engineering. I've been an engineer at JPL for about 5 years now, and I originally grew up on the East Coast. So I grew up playing a lot of sports, really enjoyed science in school, but I also really enjoyed art. So I grew up doing dance and painting and art, and so I think both are super important and make for better engineers. So once I moved into my higher education, I graduated from college with a mechanical engineering degree and moved out to California with my sister and started at JPL. And my background at JPL has mainly been in small payloads or small spacecrafts. So my first project out here was a CubeSat called RainCube, and had some projects after that, and then landed on the Mars helicopter mission. So yes, I'll be talking to you guys about my work on the project, how it developed, and then our future plans now that we're on Mars.
Awesome. We're so lucky to have you. Really, really appreciate you taking the time. I know that there's so much going on right now. And perhaps the best way to get us started is we actually have a few student submitted questions. So could we see the first question?
Hi, I'm Rashid Salam, and I'm from Carpenter Community Charter, and I have a question. How long does it take to build a helicopter that flies around Mars?
This is such a good intro question because I came on the project in 2017. But to answer your question, the beginning of helicopter started in 2014, and that was with our first prototype model, which wanted to show how we wanted to show the feasibility in lift. Like, can we lift on in a Martian atmosphere? And so that was the first step of the project. And then we launched in 2020. So total start to finish was 6 years. But the design phase took a little bit longer because there's different iterations or different types of models we have to build in order to validate our design before we can really build the flight one and get going on that. So it wasn't until 2018 that we actually started to build the flight model, tested it, design was complete, and we launched in 2020. So total six years, but probably build time was about 2 years, a little less.
Yeah, that's actually really helpful to hear. You think about something that's so small, you wouldn't think it would take so long to build, but this is something so incredibly new, and that design phase took up a lot of time, which actually kind of leads well into our second question, if we could hear that one.
Hi, I'm Eva. I'm in first grade. I have a question for you. Why is there two propellers stacked on top of each other on the helicopter? Bye!
This is a really good question and requires a little bit of an advanced answer, but I love the question. And the short answer is that two propellers stacked on top of each other creates a more stable overall system. So if you had one propeller rotating in one direction, Newton's first law of physics tells us if for every action there's an equal and opposite reaction. And that plays a little bit into this answer. So a single propeller rotates in one direction, and whatever you're trying to carry is trying to compensate and goes in the other direction. And so having two counter-rotating propellers stacked on the same axis allows for the overall force of those two to cancel each other out, so that you have a more stable system, and the thing that you care about and you're trying to lift doesn't rattle around.
Wow. I'm sure that took a lot of time of testing as well to get that one, but I imagine you'll tell us a little bit more about that. Um, We have a third student question, this one coming from a high school student, if we could see that.
Hi, my name is Mia Juarez, and I am a high school student. And my question for NASA is, are the materials used for the helicopter the same as a typical drone or helicopter on Earth? And what kind of impact will this helicopter flight have on your studies and research?
Another great question. So the helicopter is primarily made of composite material, which is carbon fiber and super lightweight, but also really strong. And the reason for that is because we want to minimize our mass, but still retain the same structural integrity. So to answer your question, yes, the carbon fiber material is actually becoming more used in aerospace today, in drones and in aircraft, for that very reason. And some of our future research will delve more into how we develop this carbon fiber in a more efficient way. So yes, great question.
It's always nice to see too how much some of the research that we do at NASA is used in spin-offs in other sectors as well. So even though you're part of a mission to Mars, the technology might actually be used in other types of flight as well. We have one more question from a student, and that might kind of lead us well into the rest of the presentation. So if we could see that one.
Hello, my name is Andrea Jimenez, and I am a junior attending Esperanza College Prep. And this is my question for NASA. We saw what you did with the rover, and now we're about to see the first flight of the helicopter. What's the next step? Thank you.
Yeah, so I'll answer this in twofold, a little bit on the rover side, a little bit on the helicopter side. So the rover, one of the main features of the rover is the sample caching system. And so that allows us to drill into the soil, create samples, and then cache them or throw them back onto the surface. And that leaves a door open for future missions to Mars to then use those samples and retrieve them and test them. So that's kind of one of the future missions and goals that we're looking for, that the rover contributes to. On the helicopter side, the helicopter is considered a technology demonstration. And so if we can successfully prove that we can fly in a completely different atmosphere than what we're used to, then that'll usher in a new wave of technology across the board for future space exploration. And future helicopters can become more capable, being able to take science data or scout different terrains and communicate to the rover. So pretty much sky's the limit on the helicopter.
Awesome. Thank you so much for going through these student questions. We received so many throughout the first few weeks of the Mission to Mars Student Challenge, so we're really happy to get a chance to address some of these in this extra session. I know you prepared some slides for us to kind of walk us through some of the ins and outs of this helicopter and what we can expect next as we prepare for this first demonstration flight. So I'd love to hear more. I'd love to turn it back over to you.
Yeah, awesome. I'd be happy to. So the first slide just kind of is a nice action shot of the helicopter, but we can skip to slide 2 and I'll give you a little bit of a better understanding of how we entered on the rover and where we're placed. So slide 2 shows the Perseverance rover from the bottom side. And on the bottom there, you can see those blades, and that's where our helicopter is sitting. So when we landed on the surface of Mars, we're considered on the belly pan or the underside of the rover. And what this image doesn't show is that we have a debris shield when we land, typically, so that protects us. And now we're at the point where the debris shield, now that we've landed on Mars successfully, we kick off the debris shield, we deploy off the rover, and then that pretty much kicks off the adventures of helicopter. So the next slide, slide 3, shows a nice video that is nice and cool to give you guys an overview. So as I mentioned, this is a technology demonstration. And typically what happens with this, we just want to show that we can fly. And so that means the helicopter is equipped with some cameras, but the main goal is flight. So it's pretty bare bones as far as any additional science or capability. So once we get off the rover drives a safe distance away. We spin up, we hover, we take some nice pictures, and then we touch back down. And that's considered our minimum success criteria. From that point on, we can do more advanced flight paths like are shown in the video. Awesome. So let's take a closer look at the helicopter. Let's skip to slide 4. And this shows the Ingenuity helicopter up close. This is the actual flight model that's currently on Mars. And just to give you kind of an overview from the top down, that top panel is considered our solar panel, and that's where we can regenerate our batteries by getting our energy source. And then underneath of that are the 2 counter-rotating propellers. And what's really interesting about this is that from tip to tip, they're about 1.2 meters, which is about 4 feet equivalent for something that weighs only 4 pounds. So that just goes to show you the type of proportional differences we have to make in the design in order to lift something on in such a thin atmosphere. Another thing that contributes to being able to generate lift is our revolutions per minute. So we have to spin up these blades really fast to somewhere close to 2,400 RPM. And all of the materials that you can visibly see here, it's all in black, is what I was describing earlier as the composite material or carbon fiber. Within that shiny box is kind of the brain of the helicopter, and that's where all of our electronics reside along with the battery. So one of my later slides will show a little bit more detail on that, but for now, let's go to slide 5. Okay, so I know I spoke a little bit about how different Mars is from Earth, but here are some numbers so you can kind of get a better understanding. So Mars atmosphere is very thin. It's about 1% of Earth's atmospheric density, which is equivalent to 100,000 feet elevation here. So that's one of the main challenges in being able to fly in such a different environment. And then Mars is also a lot colder than Earth. So the nights can get down to negative 90 degrees Celsius. So we not only have to build something that can fly, but it also has to be robust and strong enough to be able to survive under such harsh environments. And then one of the other things to note here is that the helicopter is completely autonomous. So some people ask me like, oh, is there like a person with a joystick or something flying it? And all of it is commanded through what we call the base station. And the base station is an electronics box that resides on the rover. And that's what the helicopter communicates between in order to get its commands and also downlink its data. So those are the main things that just wanted to note on this one. And then let's go to slide 6 for the big question that we had to answer. Can one really lift a helicopter in the thin Martian atmosphere? So slide 7 shows a nice video. And this was our 2014 attempt to show feasibility of lift. So this model is kind of a scaled down model of what our current helicopter looks like, and it's in a 25-foot chamber that simulates the same atmospheric density as Mars. And as you can see, it is lifting. It bounces around, not super controlled, but we actually had a certified drone pilot trying to drive this helicopter and fly it. And as you can see, it's not very controlled. So that's why we moved into a more computer-based control method. That's really because something this fragile as far as being able to lift up was not easily controlled with a human's reaction time. So to answer the question, yeah, we can lift, but now can we control it and be stable? So to build upon that, slide 8 kind of touches on that. Can one fly a helicopter in a controlled manner in Martian atmosphere? And also, can one build the helicopters to survive the environment and operate and fly as designed at Mars? So let's go to slide 9. And this will show the engineering model that we built. So one of the questions earlier was asking how long did it take to design and build? So one of the parts of designing something is being able to build prototypes, or what we call engineering models, and test them, and then make modifications to the design in order to implement for the flight model. And so this is one of our engineering models here, and you can see that the shiny box that was on the first one is now removed, so you can see a little bit more of the inside of what the helicopter looks like. And so you can see there are some electronics boards, and then within that box of electronics boards is actually where the batteries are. And this model has to undergo the same requirements as the flight one. So we built this first and tested it. And let's go to slide 11 to see the video to show how it all turned out. So once again, this is, a couple years later, 2018. We have our flight model after many iterations of the design. And this is an autonomous flight inside our 25-foot chamber. And we have atmospheric density at Mars level. And then we also have a gravity offload system, which is like a way to compensate for the difference of Earth's gravity versus Mars. And essentially what that is a tensioning mechanism that allows for that offset. So it doesn't actually lift the helicopter, but it's there to simulate that gravity offset. So we sent these commands that are coming down on the left side of the screen to run the helicopter. And as you can see, it's pretty stable. And so each of these maneuvers will play into our future planned flights. Nice touchdown. All right, so speaking of those flights, let's go on to the next slide. And this slide outlines the 5 flight paths that we have tentatively. So the first 3 flights are a little bit more solidified, but like I said before, the first flight is actually our minimum success criteria. So the first flight is going to be, we ascend about 10 meters off the ground, we hover, we take a photo, and then we touch back down. And then once we have successfully done that, then we can move on to the next flight, and that will be they'll be flying a little higher, do a translating motion in the air, and then come back down. And then the third flight will be to fly a further distance away, take some images of potential new landing zones, and then come back down to the same landing area. So contingent upon these 3 successes, we have 4 planned flights, 4 and 5, and those involve a little bit more advanced choreography of the flight. So it'll be finding a new landing zone to go to, or flying off and maybe searching for new terrain. So those are our preliminary steps in our future flight paths. One thing I want to emphasize, and that's been really like near and dear to the project, is considering this is less of a drone and more of like a Wright Brothers moment. It's really something that is completely customizable. So even though there are commercial parts that are a part of the helicopter design, they're integrated in such a way that it is truly unique. And it really is a moment in history to be able to fly in a completely new atmosphere. And I'm just really excited. I'm really excited that I got the chance to be a part of this project. So I know one of the questions said, what were some of the future things that the helicopter, what's next? And so this slide 14 pretty much shows how we've evolved in space technology since the beginning. So we started with orbiters, and then we went to landers. We have rovers that are getting more and more advanced, and now we can move into helicopters. Aerial vehicles will be a new kind of jumping off point. And slide 15 pretty much shows the team. In the center there is our fearless leader, Mimi Ung, the project manager, and then to Her left, or to the left, I guess her right, is Bob Balaram. And he's the chief engineer that asked this question, like, can we fly on Mars? And the rest of us were just called to action to make it so. So yeah, my role has really just been to help assemble the helicopter, to support all the tests that it went through, and to be a constant cheerleader for its future mission. So thank you so much.
Thank you. I mean, there's so many like motivating points in there. Seeing the evolution of Mars exploration, you look at the time that advancement has taken, and I mean, it's like breakneck, right? To think that, you know, we went from Sojourner to helicopter, right? In you know, just over 20 years. I mean, it's amazing, and I hope that people at home find that incredible too. By the time, you know, students are working at NASA, who knows? Like, we couldn't even imagine what will come next at this pace. And I think it's really important that you highlighted, you know, kind of that first test video and what failure looked like, because it's certainly not the kind of thing you get right on the first time. We're inventing something that's never been done before, and that takes trial and error. So I thought that was really, really motivating. So before we close out, I did want to show a few slides on how you at home, whether you're a parent or an educator or a student, there are still ways that you can participate in all of these events as we continue to explore Mars. On my first slide, you'll see the website for the Mission to Mars Student Challenge. Well, this was running live. It is still available, so feel free to start anytime. If you're an educator or running a summer camp, you can see there are week-by-week activities for you to do, all separated by grade level, so you can tailor it exactly to your audience. On slide 2, you'll see that the Mission to Mars Student Challenge had over 1.1 million students participate worldwide. Each one of them has a little introductory video, kind of introducing some of the concepts from my good colleague Lyle Tavernier. And on slide 3, you'll see exactly how we've kind of marched through each of these weeks. And it's been really, really exciting for all of us at NASA to see all of the student work come in and be part of your exploration. This begins with learning about Mars. You know, we want to know where we're going and why. On slide 4, you'll see that we start to plan our mission. How are we going to get there? What are we going to bring, and what do we want to accomplish? This includes kind of this conceptual idea of designing a spacecraft to accomplish your goals. On slide 5, you'll see that we start to build that spacecraft, and that in itself is not the first step, right? And this is important to communicate to students, that the ideation phase is important too, and we don't just walk out into the lab and get started building. But you can see so many really cool designs came in over the course of the last 5 weeks. Everyone's favorite, of course, is on slide 6, when you get to launch your mission and sending this off from Earth into Mars, whether you're doing that with stomp rockets or balloons or straw rockets. So many great ways to get kids excited in terms of what liftoff really means. On slide 7, you'll see that we're now prepared to land safely. Some of us land more safely than others, in looking at our student samples here. And then finally, on slide 8, you'll see that we begin the surface operations like we're doing now. So we're finally at this point where we've landed safely. The tests for the rover are complete. We can drive. Instruments are operational. And now we're ready to test out this helicopter, this completely wild, you know, kind of proof of concept flight that's really never been attempted before. So I encourage you guys to still be part of this. You can always submit your work just as these students did. As you'll see on slide 9, we have a student showcase. So you can send us your work and have it put on the NASA Education webpage, and keep us appraised. Let us be part of your exploration of what it takes to you know, build and design and send a mission to Mars. So with that, I'm so grateful for your time today. Thank you so much to our amazing guest speaker. We're so looking forward to this first flight and hopefully several other flights to come. So thank you guys all so much for your time today, and happy exploring on your own missions to Mars. Thanks so much.
Hi everyone, I'm Emily Calandrelli, otherwise known as the Space Gal, and in anticipation of Ingenuity's first flight, I'm going to teach you how to make your own paper Mars helicopter. You'll need this template and a pair of scissors. This has 2 helicopters on 1 page. Cut along the dotted lines and fold along the solid lines. Make sure flaps A and B are folded in opposite directions. Fold X and Y inward so they overlap. And then just fold this last part, Z, upward. And now it's ready to fly. Bring it up high and let it fly. Don't be afraid to get creative. Make A and B shorter or longer, add a payload or a weight to your helicopter, and then see how it affects how it flies. Science is all about trial and error, so don't be afraid to innovate and make your helicopter your own.